Hi, it's Josh again with a quick tutorial to support this geometry lesson. It's a little bit unorthodox, but I do hope you enjoy what I'd like to share with you today on a way of getting ready for your SAT for geometry. I'm going to digress a little bit and talk about written language. As an introduction, let's say we have alphabetic systems of language, like English, we have A to Z. And there's also a logographic systems. I think used to be called like picture languages or hieroglyphics, for example, like Egyptians. But also Chinese is a logographic system. So here what I've done is I've drawn two parallel lines. And we know that in geometry, if we provide paper for you, that here's some parallel lines that will never meet, but we can work within the ground line or earth line and the sky line or the heaven line. And here's the letters A, B, C, D, E written in between the sky line and the earth line. Notice that you did learn to do this when you learned the English language years ago. And what the teacher would do, the teacher would come over and she or he would, go over to the sky line and give a check mark if you did your ABCs correctly. Here, D is backwards. So you put an X above that letter and then give you a check for the letter E. And the teacher would say, okay, pretty good. You got 4 out of 5, try again. Furthermore, we then express words with syllables such as cat. Here I have a capital C, a T, and if you can read it, the English language, this alphabetic system, teacher would come over and again, up on the top line there, on the skyline, would put a little check mark there that you spelled cat correctly. With logographic systems, it's a little bit different. What you need to do is you need to get familiar with a group of basic shapes, basic elements or radicals. And for example, here's the basic shape for above, which is looks like an upside down T with a level extended up above. And then for below, the line is really right below the skyline, and then a descending column and a diagonal pointing down towards the earth is the radical for below. And then for the earth itself, you have an earth line, and then you have the a column and a vertical and a horizontal line crossing here. And the thing is that a lot of the shapes are very basic for basic words. For example, for person, it's just 2 character strokes for that character. As you can see here, for water, there's 3 basic brush strokes when you write that. The tree actually looks like a tree, sort of pictographically. It looks like it's got roots somewhere there towards the earth line, but then also it spreads out like a tree does. Furthermore, a teacher would come over, just like your elementary school teacher, if you learned English, and would go to the skyline and give a check for each of the characters as you learn to master them. As you can see, the water character that I drew the left side a little bit improperly. It should look more like a 7 or more like here going down at an angle to the left. So I've redrawn it like the teacher would redraw it above for a student to correct. Like that's not bad, but to write it neater with your brush or pen, you would clean up the left side of that character. The other thing that's amazing about logographic systems is that they're like compound words. They're used in combination. So after you learn a few hundred of these logos, then you can combine them into more complicated words. For example, tree is a single tree. And as a basic example, 3 trees is a forest. So if you draw 3 smaller trees stacked in a triangle, you now know a new word for forest. Again, what these systems of language have in common is they have the bottom line, the earth line, and also the line up above, the sky line, which is monitored with the teacher feedback in both language, basic language systems. Similarly with numbers, here I've drawn the numbers in Arabic numerals from 1 to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 with one error. And also in the logographic system, 1, 2, 3, 4 looks like a little rice bowl, 5, 6, 7, 8, 9, and 10 is a basic crossing. You can see here the teacher would come over and they go, hey, pretty good. You know, you wrote the numbers correctly. 9 is backwards. You want the stem that's coming down from 9 to be on the opposite side. So the teacher would mark up here on the skyline and the student should keep working. And here these characters in Chinese, as you can see, are sort of similar to the ones below. In fact, if you had a calligraphy brush, you can see that the way the brush strokes are, if you use the ink, we're going to do the first line here and then zig down here to write the second line. So it's 2 is very similar to the Arabic 2. Similarly, 3 is made up of 3 lines, but they're not connected. But if we had a large ink brush, it's no stretch of the imagination that it's very close to the Arabic number 3. Furthermore, in alphabetic systems, we do have placeholders in Arabic numerals. So we have the tens column and the ones column. So we can express numbers like 15, 34, 98, or May 4th along our infinite storyline here, these 2 parallels. And we can easily read them if we're familiar with the alphabetic language. What's different in the Chinese logographic language, for example, is between the parallels. You can write 10 plus 5 for 15, so that's pretty much the same. But there is no real placeholder. So instead of writing the numbers 3 and 4 next to each other, we write 3 tens and then the 4, meaning 34 for 34, and 9 tens, and then 8 for 98. So you can see as I've circled here, we understand in our place value system that that's 30 and that's 90, but here we actually write it as 3 times 10 and so on. Similarly, we're used to writing the month first and then the day, for example, May 4th, but in Chinese, and as a student who went to school in Chinatown here in New York, we would wake up and we'd write in English and also in Chinese when we got to school, and we'd write in our notebooks like for the 4th day. So we'd write the number 4, the character for sun, and the number 5 and the character for moon, which we'd interpret as the 4th day of the 5th month of the year. And now those are the radicals for sun and moon. Well, written language and understanding how much you've already learned that you may take for granted is a good way to also learn systems of geometry, from simple shapes to more complicated shapes. So let's start here with the parallel lines again. And here I've drawn a rectangle in the area on the left of the parallel. And again, they extend from left to right like an infinite storyline, that never-ending storyline for you. And you can see we start with the basic idea that the area here between the parallels, located right here, is base times height. So we do know that rectangles have 490-degree corners. However, if I go to one of the corners, here I'll go to the skyline, and I'm going to just march forward from the skyline. I'm going to shift forward to point X, and I'll mark it with an X here on the top line. So the lines are still parallel, but I'll draw a connect from the skyline down to the earth line corner here, creating this right triangle, right? Next thing I'll do is I'm going to pick up that right triangle on the left and move it to the right side in place. So I noted that with a green arrow. So now the rectangle is a parallelogram. But just like in elementary school, if you were given a piece of construction paper and the teacher says, here, take the scissors and cut off a right triangle from the corner to the, from the top down to the corner, we can move that triangle to the right side, meaning that it's the same amount of construction paper. So that's the reason why the area of a parallelogram is just like the rectangle. The area is base times height. On the next set of parallel lines, I'm going to start with the parallelogram. Now we already know that the area of a parallelogram is base times height because we proved it above. We're just moving that little piece of construction paper from the left to the right side. The top and the bottom are still parallel. And now the left, that hypotenuse is now the hypotenuse here. So we already know that those lines are parallel as well. Well, we start with the fact that this red parallelogram is base times height. But if I draw the diagonal here I'm drawing from the skyline to the earth line, or if I start on the left side, if I bookend here on the left, then from the left side up to the right side, that will split it into two congruent triangles, because we know the parallelograms are side side and that third side is reflective. So by side, 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 we have two equal triangles. Furthermore, that means that each triangle is half of the parallelogram, and it yields the formula. The area of any triangle is a half of the base height, because it's a half of the parallelogram or rectangle, right? When you draw the diagonal. So that's, it'll always be just put a half in front of base height, and we're done. Let's go on to the third line. Similarly, we can start with the parallelogram, which we know the area is base times height. But again, I'm going to go up to the top line, and it's not where that top parallel. I'm going to shift forward again and create a mark called base 1, right? Just like I drew that green arrow before, now I'm just drawing a mark base 1. But then I'll go down to the opposite corner of the second parallel, and going in reverse direction, I'll mark off that same distance, base 1. The remaining top side is the orange arrow. The remaining bottom side is the orange arrow. So now, since we've split the top side into two pieces, we'll call that base 1 and base 2. Down on the earth line, if we're reading from left to right, that's in reverse. That's base 2 and base 1. If we now draw the transversal between the parallels, we have the shape that's called a trapezoid. And now the top parallel is shorter, it's just base 1, and here I've drawn it, marked it as the lower base 2. But we know that base 1 plus base 2 is the full length because of the way we constructed it. Well, that means that the area of a trapezoid is still a half the base times the height, but the base is expressed as base 1 plus base 2, because they now can be of different measurements. So there you have it. Starting with the rectangle, we can generate along the parallels by shifting forwards or backwards. We can create the parallelogram, the triangle, and the trapezoid. And so there they are. Just to recap, the rectangle has an area of base times height. The parallelogram also has an area of base times height. The triangle has an area of a half base times height. And the trapezoid has an area of a half base 1 plus base 2 times the height. Lastly, as the basic shape that we need for SAT prep, that's most common in the problems, is we need to know that the full circle area for area compositions is pi r squared. Well, once you start with that fact, even if it's a complicated design by an architect or bay window or whatever the other common problems are in the SAT, we can see relative to the full circle, the three most common shapes will be a 3/4 circle, a semicircle, or a quarter circle. To find those areas, simply lock in place the appropriate fraction in front of pi r squared. Here we go. So for the 3/4 circle, we have the area is 3/4 pi r squared. For the semicircle, the area is a half pi r squared. And for the quarter circle, the area is a 1/4 pi r squared. I hope this introduction to the basic elements that are in area compositions is useful to you in your SAT prep. Thanks for watching my video. Good luck.